This is Bill Farmer again. Welcome to McMaster University course Computer Science 1JC3 Introduction to Computational Thinking. Today we're going to start a new topic called Algebraic data types. We're going to start with a review question. In a previous lecture we talked about a function called linear search, which searches linearly through a list. And it takes here three arguments: a value, a list of the same kind of values, and a predicate which takes two of these values. So A here can be any type. And when we apply this function to x, y, and z, the question is, what role does z play? And I'm going to give you a moment to think about it. You can turn off your video, come up with the answer. Okay, well, welcome back. The answer is B. So Z, its purpose is to check whether X matches a value in Y. So Z is going to be applied to X and Y. And if it returns true, we have a match. If it returns false, we do not have a match. Okay, so I want to next talk about an example of solving a problem with recursion. So we talked a lot about recursion. Let's sort of review how you would solve a problem by recursion. And the problem we have here is we want to define a function of this type. This function takes an integer and a list of integers and returns bool. So what is it going to do? Well, if we give this function x and l, it's going to return true if x occurs in l. And it's going to return false if x does not occur in l. So that's how it works. But we are going to assume that the members of L are in ascending order. So they're ordered. They're ordered from smallest to biggest. And this will greatly affect how we might solve the problem. So if we're going to solve this problem by recursion, in other words, we need to define the function using recursion, here's what we're going to do. We're going to figure out what are the simplest cases, and then we're going to figure out how to take a non-simplest case and reduce it to simpler cases. And then, to check that our definition makes sense, we're going to assign natural numbers to the input, which is this pair, and our assignment should show that the definition is well defined. That means that whenever we have a recursive call, the inputs for those recursive call will go down in complexity. They will be assigned, in other words, a smaller natural number. Now there are two solutions that are possible. The first one is linear search. So let's review how that works. So with linear search, I'm going to have my list here. Let's say I have a list of numbers like this. Notice it's in ascending order. How do I solve the problem? Well, the simplest case equals the empty list, because we know immediately that means we're going to return false, because there's going to be no member. We can't find the member in the list because there are no members in the list. And then we're going to break it down to the non-simplest case. Here we're going to break it down into checking the first member and then applying our function to what's left. Now this is linear search. Basically, we go through here and see if we can find the value we're looking for. Starting from left, going to the right. Now a different approach is what is called binary search. And the way binary search works is I basically, instead of looking from the left and working my way through, I jump to the middle, or as close to the middle as I can get, let's say to this spot. And then I check to see if my number that I'm looking for is bigger or smaller than that. Let's say I'm looking for the number 9. So 9 is less than 12, and that means my non-simplest case is going to be, it's going to be all the members that are going to be smaller than 12, because I know 9 is smaller than 12. And so basically I cut my list in half. And I do this over and over again. So then I'll pick a middle spot, let's say this, and now I know that 9 is bigger than that, and so I go like this, and then I'll pick one of these two members. Let's say I pick 12. I know 9 is smaller than that, so I pick 8, and now I know 9 is bigger than 8, so I know 9 does not occur in the list. This is called binary search. It is much more efficient than linear search. But it requires something important. It requires that the members of L are in ascending order. Okay, so that's a little exercise of rethinking about how we solve a problem by recursion. Okay, so we're going to be talking in this topic about types in Haskell. Types are very useful. They help us organize how we define functions, and they help us find type errors. Type errors are when basically we try to apply a function to a value that's not meant for that function. So type errors are very common in programming. In Haskell, we can catch all these type errors before we run our program by letting the compiler do type checking. So in Haskell, an important part of developing a program is creating the types that we need, the right types for the task at hand. And there's basically two ways of doing this. One way is we can create a new name, we can give a new name to an old type. And I'll explain how to do this. And the second way, we can create a completely new type of new values. And so this is a powerful thing. We don't have to use just the types that Haskell provides us. We can create new types. This is where the idea of algebraic data types comes in. Okay, so let's talk about synonym types. So a synonym type is just a new name for an old type. So when we define it, it's going to look like this. Here's the new name. Here's the old type. And once we make one of these declarations, these type declarations, then we can use that new type, the name for the new type, wherever we had, I should say that we can use the new name wherever we could use the old type. So here's an example. We could say that vector is a synonym for the triple of doubles. So whenever we need the type, which is a triple of doubles, we can use instead vector. So actually we could either use this or this. But when we want to think of a triple of doubles as a vector, we're going to use vector type. So synonym types are very simple. You're just creating names that stand for types that already exist. Now, what's nice about synonym types is these types can have parameters. So I can have a type declaration like this, and I can list parameters, and these parameters presumably occur in my old type. Everything works the same, and this gives us a polymorphic type. So new type can take on different, it's a name for a whole family of types. So here's an example, similar to the one before. So when I use the name, the parameterized name, vector A, what that stands for is a triple of values of type A. And A here is a type variable. So this is very convenient. It says whenever I want to think of a triple of 3 values of the same type as a vector, I can use this type. Okay, so that's synonym types with parameters. Now let's go to the really important notion in this topic, algebraic data types. Now we're going to call these just algebraic types for short. In general, instead of saying data type, we're just going to say type. So this is a new type of values which is formed as a sum of products. And we'll explain later what a sum is and what a product is. And it is defined by a data declaration. So it's a declaration that starts with data, and it has a number of expressions listed here, and they're separated by these bars. Now, we're talking about it in abstract. We're going to see several examples later. But these T's here are all types. So we're going to define a new type from old types. And the C's are constructors, value constructors. They allow us to construct new values from old values. So for instance, if we look at C1 takes M1 different types. So C1, if we give it values from these M1 types, so the first value would be of type T11, and the last value would be T1M1. So if we give values from those types, and we give it to C1, it constructs a new piece of data. It constructs, in other words, a new value. So these are the crucial part of, let me change the color here. These are the crucial part of an algebraic type, these value constructors. And as I mentioned, all these T's are types, but the interesting thing is these T's can include the type T that we're defining. And another point to mention is constructors do not have to take arguments. They can have no arguments. And the type of a constructor looks like this. It's going to be a function, and the function takes these arguments and gives back the type T. Now, it's a type of a function, but it's a very special kind of function, because this function, we don't think of it as doing a computation and computing a value. We think of it as constructing a value. Okay, so let's move on. The interesting thing is, each member of this type T that we define is constructed from the constructors in exactly one way. So I have these constructors, I can put them together and construct things. Every member of T is constructed in exactly one way. And no member of T, there's no member of T that is not constructed this way. So the constructors give us exactly the members of T. And so there's a slogan that goes with this called no junk. No junk means that every member of T is constructed from the constructors. There's no junk. There are no members that are not constructed in this way. And no confusion. Because no confusion says if we have a member of T, it can only be constructed in one way. So there's no confusion. We can't construct members in more than one way. Okay, so once we have an algebraic data type, now we can define functions in T using pattern matching with respect to these value constructors. So basically, the values, if you think about them a moment, the values are going to be things that we construct with C1, C2, and C4, or Cn. And so if we have n constructors, we're going to have at least n patterns. And if we're going to define a function on T, we can define it by pattern matching using these n patterns. This is very convenient. Now, algebraic types are also called inductive types. So keep that in mind. And once we define an algebraic type, it induces an induction principle. So this is a principle for how we prove a statement about all members of T. And I'll just point out, and this is something you'll see in subsequent classes, proof by induction is the most powerful proof technique employed in computing. And the reason for this is in computing, we use inductive types all the time. Inductive types, or what they're called in Haskell, algebraic types. We use these types all the time in computing. Each of these types has an induction principle. We use the induction principle to prove statements about the members of these types. Okay, so I mentioned that an algebraic type, you can think of it as a sum of product types. So what is a sum type? A sum type is pretty simple. It is an algebraic type that has more than one constructor. And so each constructor sort of gives a subclass of values. And here's a very simple example of an algebraic type called bool. And bool has two constructors, false and true. And notice that these constructors do not take any arguments. There's no other types mentioned here. And so false stands for a value, true stands for a value. The new type we have just constructed has two values, false and true. And this would be a type that we could construct if we want to be able to have functions that deal with Booleans. So that is maybe the simplest example that we could ever think of a sum type. So all a sum type is a type that has multiple constructors. Now a product type is an algebraic type that has one constructor and it has essentially the same structure as a tuple type. And these tuple types correspond to what people call Cartesian products. So if I had, let's say I had this type, this tuple type in Haskell. In normal mathematics, we would think of this as a Cartesian product. It's basically the same thing. So that's why these are called product types. They correspond to Cartesian products. So here's an example. We could create a new type called point. We have one constructor, therefore it's a product type, make point, and it takes two arguments. It takes a float, and it takes a float and gives back a point. And this new algebraic type we created, it has the same structure as this tuple type. So you may say, well, why do we need this product type? Well, you don't really need it. You could use just this tuple type, this type of ordered pairs, float and float. But notice here that we can name our constructor. That can be convenient. Okay, so that's what sum and product types are. We're going to stop here, and then we're going to continue with more algebraic types in our next lecture. So thank you very much. See you next time.